we've done a little bit with trig, and we've done piecewise function stuff, so I brought them together in a piecewise function. And the instructions are to identify the values of c for which the limit does not exist. So, what are your initial thoughts on this? How are we going to find those values of c for which the limit does not exist? What do you think, Andy? Okay, so immediately, based on what we've done with piecewise functions, there's a concern as to whether or not the limit is going to exist anytime we jump from one function to the next. So at 0, we want to see if the limit as x approaches 0 poses a problem, and also the limit as x approaches pi. Okay, so we've kind of got two things to think about there. Anything else? Any other potential case other than where we jump from one piece of piecewise to another? I guess why or why not? So you guys are saying no, there's no other place we have to be worried about. Why do you know that there's no other place to do Yeah, that's one possibility. What type do you have on my book? Right, so you just quickly glance at the three functions that are making up this piecewise. As an individual function, sine of x is continuous forever, and there will never be a limit issue with just the sine graph. There's never a limit issue for the 1 minus cosine graph, because that's just the cosine curve flipped and shifted up 1, and then the plain old cosine curve. Those are all continuous functions that will have no limit issues, no asymptotes, no jumps. So it is possible that if I took this out and made it like 5 over x plus 2, we would still have to check 0 and pi, but negative 2 would also be a concern as well, because negative 2 is a vertical asymptote, and therefore the limit wouldn't exist there, and negative 2 falls in that interval, so we have to be concerned. If I had 5 over x minus 2, 2 would be an asymptote of this, but we wouldn't have to worry about 2 because it's not in the interval. So a quick glance at the type of functions we're dealing with within the piecewise function will potentially make another place of concern. But we don't have that here. We just have at the 0 and at the pi. So how do we find the limit as x approaches 0? Dakota, if the limit is going to exist, it has to be the same as you approach from the what and the what? Left and right. So we kind of need to look at that. We need to look at the limit as we approach 0 from the left, and we need to look at the limit as we approach 0 from the right. And with a piecewise function, we can do that. The left of 0 would be this equation. So we would just take the sine of 0, which is 0. If we're approaching 0 from the right, we're dealing with the second piece of this. So plugging 0 in there would make 1 minus the cosine of 0, which is 1 minus 1, which is also 0. So the limit from the left matches the limit from the right, so that limit does exist. So that is not a value of c. Our limit does exist there. It is 0. On the other one, similar concept, we're looking for the limit as x approaches pi from the left and the limit as x approaches pi from the right. So to the left of pi means less than pi, which is equation 2. 1 minus the cosine of pi. 1 minus, what's the cosine of pi? Negative 1. And then 1 plus 1 is 2. If if we're approaching pi from the right, that's when x is greater than pi. So plug in pi here, that's just cosine of pi, and the cosine of pi we said is -1. So those do not equal each other, which means this limit does not exist. So that is the one and only value at which this limit does not exist. So the value of c is pi would be your answer. So again, working on our familiarity with how piecewise functions throw a little wrench at us. Okay, on the next example, you're asked to sketch a function that satisfies this criteria. So I want you all to take a minute on your own to try to do that because there's a boatload of options. And I will wait to collect a few of yours. Nope, you don't have to write a function. And we'll go through our checklist of criteria. On this first one, is f of -2 0? Yes, it is. Is f of +2 0? Yes, it is. Is the limit of the function as x approaches -2 0? Yes. Is the limit of the function as x approaches 2 does not exist? Yes. So this is good. Any questions on that person's graph? Okay. Is this one's f of -2 0? Yes. Is there f of +2 0? Yes. Is there limit as they approach -2 0? Is there limit as they approach +2 undefined? Yes. Because from the left and from the right, it's different. 2 for 2. And on this one, is there f of -2 0? Is f of +2 0? Is there limit as they approach -2 0? Is there limit as they approach +2 undefined? Yes, differently than the others were undefined, because the others just had a jump, and this has a jump but also has a totally removed point. So that's just the rest of the function going that way. So we have an open circle at the end of this piece and an open circle at the start of this piece, but the function value is still 0 at 2. Good question. What if this wasn't up here? Chris, zip it, please. What if this didn't exist? A great question. Is that still correct? Is f of 2 still 0? Yes, because they have a point here. And is the limit as it approaches 2 does not exist? Yes, because for a different reason. Because it exists from the left, but now it doesn't exist at all from the right, so there's no way the overall limit can exist. Versus before, it existed from the left, it existed from the right, but they were just flat out different. So yes, that would still be correct. Good job. Anybody else have one that they're curious if it's correct? Or want some feedback on? Send that over. Oh, good. We got a candidate. Okay. Does this person's f of negative 2 equal 0? Yes. Does f of positive 2 equal 0? Yes. Their limit as x approaches negative 2 is 0? Correct? Yes. Their limit as x approaches 2 does not exist. Right, that's where we fall short. Because your limit does exist as you're approaching 2. You want the limit to not exist. Now, it's not differentiable there. That's what you were thinking of. And that happens a lot where we start to get these vocab words confused because they're kind of all intertwined and so forth. So also think about where we are in this textbook. This textbook hasn't dropped the word differentiable yet. So there's a little bit of this weird time where we're overlapping from the PreCalc book, and we know more than the calculus book thinks we know. But we haven't got to derivatives or differentiating in this calc book, and we won't until chapter 2. So your limit does exist, and you confused it with differentiable because you are correct in that that would not be differentiable at 2. And we will have different types of functions drawing like that when we do get to that differentiable part, but not yet. Okay, so flip over to the back, and it's a general lit question, and I just scanned, I haven't put it on my website yet, but I just scanned the review sheet for the test. So I took any and every limit question I could find, which is pretty much the whole chapter. There's like 100 plus. Now, you've probably already seen 50 of them. You may have already seen 100 of the 120 questions. But what I had to do, because there's probably 150 limit questions overall, is I had to decipher which ones can we do without a calculator. Okay, because you're not going to have a calculator for the test, so I'm trying to find all the ones that you can do without a calculator. And there are a certain pocket of ones that can only be done with a calculator. And this is one of them. So just to kind of review the steps of how to find a limit. Step 1 is direct evaluation. And if that works, there's really 3 scenarios. Either you get a numerical answer, and you're done. You'd be done. Or you get a number over 0. In which case the limit does not exist, but you might need to be more specific and determine if the answer is simply does not exist, or is it one of the infinities? Because if you directly evaluate something where there's a vertical asymptote, for example, you'll get like 5 over 0. So that tells you that the limit does not exist, but you also need to realize, oh, that's a vertical asymptote, so maybe I can give a more specific version of does not exist. And then the third scenario, which is the one that tends to come up all the time, is the indeterminate case. And if we get that indeterminate case, now there's several follow-up things we need to try anyway. So the first thing would be to try to manipulate, which can consist of factoring and canceling, or clearing fractions, or rationalizing the numerator, anything of that nature. And if you manipulate and then simplify, so manipulate/simplify, then you may be able to redirectly evaluate. So re-evaluate. But something like this one, manipulation, we haven't learned how to manipulate this. We don't even know what to do with this. Clearing fractions, rationalizing, all of those things, not an option. So the next try would be to try something that's a little bit less efficient, but sometimes the only possibility, and that would be to sketch a graph. And again with this one, we have no idea what this graph looks like. There's no parent function that we can work off of, because this is kind of a combo of an exponential function on the top and a rational function, given that it's over x, and that's just not a specific family of functions that we can take a parent graph and start shifting. And then the fourth and final non-calculator option is to play around with points and plugging them in. So kind of, even though we can't plug in 0, can we kind of brainstorm about what would happen if we plugged in something infinitely close to 0, like 0.001. So brainstorm, I'll write this down, about what happens when you evaluate a number very close to C. I'm just going to use C generically, like because we normally say x approaches some C value. In this case, our C value is 0. So if we were to brainstorm about what would happen if I were to plug in a number that's very, very small and getting closer and closer to 0. Sometimes that's possible, and sometimes it's really not, because it's too tasking. For example, this one, if I were to plug in 0.001, e to the 0.001 power divided by 2. So e to some really, really small exponent. E is like 2.7. So there's another wrench thrown at you. That's an irrational number to begin with. Now you're trying to think about what happens when you raise 2.7 to a really, really teeny tiny power. Not sure. We might be able to get a little further with that, but then after you do that, you still have to think about subtracting 1 from that. And then you're dividing it by something teeny, teeny, tiny. So there's too much going on there to really make that a practical approach. We could try it. I would probably, you can ask the other classes because I thought out loud in those classes. I would lose 90% of you in my thought process in getting there, and it's such a weak argument and such a stretch because these numbers are such that we can't really wrap our head around them without a calculator, that it's not worth it. So it doesn't really work here. We've seen plenty of examples where it does work, brainstorming about a plug-in, but not here. So when you're out of options and none of these work, your fifth and final option is only to really go to a calculator. And when I do all of these 115 questions to try to sift through what can go on a non-calculator test and what you do need a calculator to do, this is really my order of which I go through them. And if this part particularly is too taxing or even just doesn't even get you the right answer, because you're not considering all the intricacies of the type of function, I'm immediately like, okay, that would be a calculator question, and I put that on a calculator section. Okay, and this is definitely one of them. So if you have a calculator and it's a calculator section, I just want to make sure you know also how to solve this. And we talked about it in the PreCalc book, but we never really used it because we always had non-calculator assessments. So you type in the function. You're trying to see what's happening as you surround 0. So for my window, I'll go from -2 to 2 on my x-axis to surround 0. And then I just kept it a standard square window, so I made my y from -2 to 2. I might have to go back and adjust that. But that's what the function looks like. And we're trying to see what the limit is as we approach 0. First of all, does it appear as if it exists? Yes, it does. So the limit definitely exists. Now to find what it is, I use second trace and value. And I can't plug in a value at 0 because I'd get undefined. So I plug in something infinitely close to 0, like 0.00001. And the closer I get to that, the closer this is going to get to 0.5. So it's 1/2. Now by the time you reach the end of calculus, you will learn more strategies than what I'm teaching you, more shortcuts than even what I'm teaching you this year. And there is a rule out there that will help you with a function like this, but there are lots of little categories, and we're just going to keep it to kind of the main few categories here, and the main few ways we manipulate, and then next year you'll look a little bit more into examples like this. Okie doke. Okay. The next exercise here is this greatest integer function. Came up in the pre-calc book, but it's been a while. Okay. Does anybody remember? Like, let's review what this means. I'll do 4.7. If you had to evaluate that, does anyone know what that means? Or what the value of that is? We want the greatest integer less than or equal to that number, which is what? 4. For something like this, what is the greatest integer less than or equal to -2? -3. We have to go less than that, -2, which would put us to -3. So this wants us to graph the function, which we'll do it by hand, but to make it easier, I'm going to get rid of this 0.75. So just cross that out so that we don't have to deal with the decimals on top of everything else. So if I were to do like a 0, if I were to plug in 0, what's 0 minus 1? -1. And there's a negative out in front of that, so -1 is 1. What's the greatest integer function of 1? 1. And what's 18 minus 9? Well, 18 minus 9 times 1, technically. 9. So we have a point at 0, 9. What if we go just past that to 0.1? What's 0.1 minus 1? -0.9. And there's a negative in front of that, so -0.9 is what? 0.9. What is the greatest integer function on 0.9? 0. The greatest integer less than or equal to 0.9 is 0. So what's 18 minus 9 times 0? 18, right? 18 minus 9 times 0 is 18. So the moment I got past 0, this thing jumped up to 18. 18 minus 9 times 0. 9 times 0 has to come first. And then 18 minus 0 is 18. So there's an open circle at 0, 18. And then the moment I got past 0, it jumped up to 18. And that's going to last until I get to 1. Because what happens when I plug in 1 is I get 0 again. The greatest integer function on 0 is 0. So 18 minus 9 times 0 is still 18. So that's a solid circle. But the moment I go beyond 1, like 1 point anything, 1 point anything minus 1 is just that, like let's go 1.1. 1.1 minus 1 is 0.1. Then that becomes -0.1. What's the first integer less than -0.1? negative 1. So 18 minus 9 times negative 1 is 18 plus 9 is 27. So this jumps up to 27 with an open circle right at 1, but as soon as you get beyond 1, all the way up to 2, you're going to be at 27. You remember this step function? And with the step function, one end is an open circle, and we've kind of already explored which end that is, and the other end is a closed circle. Where's this next open circle going to be? 2 comma what? 36. So you've recognized the pattern of this is just increasing by 9 every time. And it's going to be that way until 3. And then it's going to jump up to 45. And it's going to be that way until 4. And this step, just to complete it, would go back to negative 1. So a reminder of step functions, and what is the limit as t approaches 3.5? So here's 3.5, which is right there. Does the limit exist at that location? Yes, it does. What is the value of it? 45. And at 3, does the limit exist at that location? No, because this is where one of our jumps is. The end of one step and the beginning of another. So the limit is different coming from the left versus coming from the right, so this one does not exist. Okay? And then we get to some true or false, which are popular types of questions and great questions in the Calc book and in Calc, because it's not concrete. And they make you think about it, and they make you read mathematical symbols, which is just a good skill to get yourself, especially those of you who are going to go on a major in math or do something in engineering or math. It's important that you can read the abstract values and make sense of it. So in number 1, it says, if the limit of a function as x approaches c is 0, then there must exist a number k such that f of k is less than 0.001. So I'm going to throw a sketch out there, and let's let c just be randomly there. I need to start this with a function so that the limit as I approach c is 0. Why don't you all right now draw your own version of any graph, any function for which the limit as we approach c is going to be 0. Try to be creative if you can, so I have like different looking functions. Draw a function so that the limit as you approach c is 0. Because in order to be true, this would have to be true for all scenarios. So I'm just going to use these. So then we have to sift through this language. So here's someone's. We can all agree that this function has a limit as x approaches c of 0. Whose is this? Is this like a parabola turned into a line? That's great. So, so she's almost got like a parabola, but the limit as we approach c is definitely 0. So the true or false part says, well then if this is the case, is there a number k such that f of k, so k is like another x value. So is there an x value such that f of that x value is less than 0.001? Is there an x value that has a y value less than 0.001? Yes. Does there have to be? Say it again. I think you're proving your answer wrong. They're saying that there has to be some case surrounding this where the y value is going to be less than 1/1000th. Well, of course it is, because if the limit is 0, that means it's getting infinitely close to a y value of 0. So will you ever be less than 0.001? Absolutely. You would be less than 0.0000001 because you're getting infinitely close. Your y value, if your limit is 0, your y coordinates are getting infinitely close to 0. So when you're infinitely close to 0, are you less than 1/1000th? Absolutely. Okay? On this one, like think about 1/1000th being right here. 0.001. Is there some x coordinate surrounding C that has that as a y coordinate? Yes. Okay, so we've got that. Again, 0.001 would be right here. I mean, of course, it all depends on our scale. That's if this is 0.005, but nonetheless, if the limit is 0, we're getting infinitely close. Okay? None of you have an open circle. I like this one. I'm just going to make it an open circle. So again, the y values are getting infinitely close to 0. So is there some x coordinate on either side, some k value, I guess is the way they're saying it, that f of that k value is 0.001 or less? Yes, has to be. Okay, the other one that I drew just to kind of pick your brain a little bit, does this have a k value on either side of C, such that f of k is less than 1/1000th? Yes. In fact, all of them qualify because they're all in the negatives. So of course they're less than 1/1000th. Okay? That was probably the hardest of the three, I think. So grab yours and take it back. That is true. On number 2, keep in mind that you're only answering true if it always has to be true. If you can find one scenario where it's false, you have to answer false. On 2, if the limit as you approach C is L, then the function value is also L. Is that always true? No, that is false. Of course it can be true. And let's go this far. If it is true, then what do you know about the function at C? Continuous. This is the definition of being continuous. So if that's true and this is true, then it's continuous, but our limit can still exist without the function value being that number as well. It would just be a discontinuous function. And then lastly, what is the, well, this says that the limit of the radical x function as x approaches 0 is 0. True or false, and then justify your answer. False, and why? Correct. Now this one is best known based on the nature of knowing the look of the graph. That's what that graph looks like. So our limit as we approach 0, we should know does not exist. Coming from the right, it's 0, but it doesn't come from the left. So that is false. Okay? On your homework tonight, I want you to look out for problems that you think you need your calculator for. Okay? There may be some. I'd have to look through it again. But if you think the only way to do it is to use your calculator, go ahead and use your calculator. But make note of it and double check with me tomorrow that there's no other way that you should know how to do. Right? Because think, or you might not remember how to manipulate it, or you might not remember how to sketch the graph, or you might not be brainstorming correctly. And I would say, no, you don't need a calculator for that. And I want you to kind of discover that. So make note of the ones that you think you have to have a calculator for, and let's run those by me tomorrow just to be sure. Okay? Maybe put a star next to them, put help, I don't know, however you want to do it.